can start manipulating data in there. So I'm going to get my data first. So this is my, I have a case class where I actually have my, this is a representation of that table we just created. So if you know Scala case class is like an object that shows, here's a structure. Here's a new thing. This is Spark SQL. Spark SQL is Hive compatible. I think you just heard about some of this. And Hive is pretty much SQL, right? This is what we, as DBAs, have been writing for a long time. Well, look what I created here. This is a select weather station ID, year, month, day, max temperature, min temperature. I now have an aggregation. Well, if you know SQL, you know that if you do an aggregation with a max and a min, you got to do a group by. So I'm grouping it by day. So every hour in that day, so all 24 hours of that data, I'm going to group by and find the min and the max inside that in one statement. That one statement then gets run right here. So I have I create a SQL statement. Spark SQL is how you run SQL statements on Spark. It figures out how to do, like Hive creates the MapReduce. Spark will create the correct RDDs for that. I put it all into a result set map that maps to this case class. And this is the magic word, collect. And when I say collect, it goes and does it. It runs it on the cluster. And that's done in parallel. So what I've essentially done here is go get me every weather station ID, and you can find the min and the max for each weather station for each day. That's a lot of data. Potentially, I have a 6 gig data set of weather. It's just 10 years of data. 14,000 weather stations. That's a lot of data to look through. This can run it pretty quickly. So this is the select, and this is what I get out of it. I'm going to run this job right here. This is when I put it back in here. Now this is a do loop, or this is a loop inside here for a session. I create a prepared statement, which is part of Cassandra, for inserting that statement, inserting those records back into Cassandra. And look what I do here. This right here, I just iterate over every result set, and I write out my weather station ID, year, month, day, my high and my low, right back into Cassandra. This is done in massive parallel per node, runs like crazy. So what do I get out of that? Now I have a fully populated table. So when I say, give me everything for, this is actually San Francisco, for 2012, the month of September, I get my results back. And it was a pretty warm, warm September. Welcome to San Francisco. So we had a 21 to a 4. That's San Francisco.
I have a question.
Yeah.
Why is it with RDD so fast? Is it because of parallelization or?
It's two things. It's parallel, massively parallel, and we'll get to the punchline of why that's important for Cassandra. But it's also in memory. It doesn't really, it will pull the data out of the disk, and now it's an immutable data set in memory. So as it's manipulating, filtering, all those operations are done strictly in memory. That's what speeds things up. Even the shuffle, if it doesn't need to shuffle, which is a hard part to do, it doesn't have to go across the wire. You can do it inside the RDD. So let's see what's the next one.
Isn't it that Mara, what is the name? MariaDB is doing the same thing as far as I know.
With Spark?
No. With basically they have in memory and as well.
MariaDB probably is. I mean, it's a relational database.
Yeah.
It probably is. Most relational databases have an in-memory workload component now.
Yeah.
It's just the parallelization. When you need to store a petabyte of data, I would not do that in MariaDB. And it's a typical problem that we have to solve now. We try to put as much into memory as possible. But you need to have a consistent data set, and you need to have it massively parallel. So what just happened here? What did we do? We have raw weather data that had our just basic, here's all the temperatures forever. We read it, we transformed it, and then we inserted it right back into this table. If you've ever had to manage an ETL job, you know that can really suck, right? Because it takes a long time to move data, it's expensive to process it, and it's expensive to put it back. This does everything in place, in memory, on the node itself. So that is being done on a locational awareness. So this is important. This is the second part of the question. Because we know what a partition ID is, we know where it is, we can actually look at the data that's on that node only. Spark can say, I'm going to look at all the data. It will break up all the pieces of data based on that token, because it can hash the keys just as well as anybody. And it'll only look at the data that's on that node. It doesn't have to scatter around and look at the entire cluster. So if I have 4 nodes of data, then each Spark master only is responsible for 1/4 of the data that it's sitting on. So if I break it into 4 chunks, they're all working on 1/4 of the data each, they can combine the results. That, at large scale, makes a big difference. And that parallelization, you can even break down those individual masters into bigger chunks. 10, 20, 100 parallel chunks. And they can iterate over in parallel because it's an immutable data set. So, switching gears, I don't want to wait. I don't want to do things in batch. I would rather have it done now. This is where streaming comes. Streaming is the best thing for the impatient, right? Because when you have ADD with your data, this is going to help. And I've built these systems, and they're so much fun. Because the data, once the data's in the system and it's all built out because of streaming, then you never touch it again. So there's another problem. I want to have up to date for today. I want to know the high and low rainfall totals. I want to know that right now. Every time I hit refresh, because that's what I do, I hit F5, F5, F5. I want to see what the high and low is right now. And that requires me to process that data from the weather station in a stream. Because I'm not going to wait till tomorrow when the batch job runs. I want it now. Okay, so Spark, you can do zillions of bytes. That's a word. But what about streaming? You can do gigabytes per second. Different problem, right? I can put gigabytes per second into the cluster, but it's not processed yet. It's not done. It's like flour, not bread. It's flour. I want to make the bread as it's coming through. That's where the gigabytes per second is with Spark streaming. So how does this work? What's that?
Do you have a network problem? How did you transfer something?
How do I get gigabytes of data?
Yeah.
I use Google. Google Compute is really fast. So we have input stream. This is a block diagram. Our input stream can come from various sources. Kafka, which I will be in Budapest in a couple of days talking about quite a bit at the ApacheCon. Love Kafka. Flume, which is another way to stream in data from logs. HDFS, Kinesis, which is like a Amazon Kafka. Twitter, yes, Twitter is now an input stream. So all of these things produce data in a order, in a stream. My weather station would probably go to an app that would have Kafka. I have a block diagram for that. But Spark streaming, what it's doing, now if you're familiar with Storm, Storm takes each new item and creates a tuple and propagates that. So each item is individually controlled. What can you not do with Storm? Aggregations. You need to put something on top of it to do an aggregation with Storm, which would be something like Trident. Trident allows you to do aggregation, but how does it do it? Microbatches. Spark streaming is all about microbatches, meaning that as data comes to Spark streaming, it creates a window. It says, here's 30 seconds of data, reduce all that data in 30 seconds. So these microbatches are ideal for things like doing aggregations, but even more important, machine learning in the stream, because I need to see a larger window of data so I can make decisions. So this is all done by the Spark engine. So that same code that I wrote to do my batch job, I can apply that to a stream. That's pretty cool. And those batches of stream data, once they're processed by Spark, the RDDs can be persisted to Cassandra. So the D stream, like RDDs are really important for Spark, D stream is really important for Spark streaming. They're all microbatches, and this is a continuous sequence of windows. Right here, these microbatches. And you can control how big that window is and how much data you want to look at inside the window. So, like here's a very simple example of that, where I do a reduce in the fly. So I take my Twitter stream, and I'm going to just take out everything that has a hashtag in it, so I can create a flat map of that and count it. But if you look right here, this is how I create my windows. So every 5 seconds, process 5 seconds worth of data. So I'm grabbing 5-second chunks and aggregating those. And that's essentially how I'm getting aggregations in that Twitter stream. I do a transform, and then I save it to Cassandra right here. Here's my count I'm putting to Cassandra based on what I did in the stream. This is all done real time. It's not a batch job. When I go to look at Cassandra, that data is ready to go. It's ready to go in a materialized view, baked, ready for my application. Yeah? That's what this is. So that when yeah, that's exactly, I'm sorry, it probably wasn't clear. When I say I want a window of 5, that's how much buffering you're going to do. You could create a window of 30 and only aggregate 5 seconds of that window, which is a sliding window at that point. I'm filling it up with, I'm analyzing as much data as I'm gathering. So this is my next area of cool, is machine learning with Spark streaming. I talked to the guy who runs machine learning for Spark. He and I got excited really fast when we started talking about the possibilities, because this is a good example. You can train your model and then apply it. So I set up my connection, and then I do a training of my data. Let's say that you're looking for suspicious keywords. You're just doing a simple Bayesian, right? Spam filtering on Twitter stream. And you're looking for hashtags that are like buy a Rolex. You could train your data set to look for that, and then apply it. If you look right here, your model, you set your streaming k-means. I'm using k-means in this case. I create my model right here, and then right down here, you know, you do an SS start. It will start looking at the stream and applying that machine learning algorithm to the stream in those batches again. So just as you were doing k-means maybe on a group of data, now you're doing it on these micro batches of data. Yeah.
If I understand the example correctly, the training data is only the training data from one micro batch. Can you continuously aggregate the training data per micro batch into a common representation? So for example, if you look at a text stream, you typically have a bag of words representation that you count for each word, the number of occurrences. So each micro batch, I get a bag of words representation. And can I aggregate this bag of words over the time?
Well, all right, so in this case, the training data is a file, right? So here's your bad words file, right? So here's all the negatives. With k-means, you may have, you have your when you create k-means, you have your good and your bad. You find that line, and say, oh, it's up here and down here. There is a way, and I don't know exactly, I don't have the code for this, but there is a way to train on the fly as well. But you need to have a negative component feedback loop, right? You have to say, oh, this new thing is bad. And that's, Bayesian's, that was spam filtering, right? You have to click on the button and say, this is spam, and it retrains. Or if you see a certain thing over and over again, you can put a filter flag on it. That might be something to think about. If I see this hash 10 times in the last second, I would like to now create that. That's now a spam. So there could be feedback controls inside of this.
But you do this for every micro batch standing alone for itself, right?
Right.
Can you basically take the result of the last micro batch, or actually all the last micro batch, and incrementally update the model, taking the new micro batch into account? So basically keep the result of the previous training and add the new information as it arrives, integrate into the model.
Yes, that's what I was trying to explain. Is that's what I would do. Like if there's data that would read or that would change my training in some way, it could be reapplied to the model. I don't have an example of how to do it. Again, this is something I've just started to get into a lot more. There are the examples online. If you go to the ML lib, there's documentation for that in the Spark streaming section. This is something that's being developed right now, really heavily. ML lib is one of the fastest moving projects in the Spark ecosystem. And Spark streaming is probably the one place it's going to make the most sense. Fraud detection, spam filtering, all sorts of things. Yeah?
Yeah, I think it's a stream, and you aggregate over chunks of the stream.
Right.
And that creates a new stream.
Right.
And you can aggregate over that as well.
Yeah, you could feed it back into itself. You could create turtles all the way down. And it's because this is code, you could take the result of that, positive or negative, based on whatever coefficient you drop out of it, and feed it back into the model. Can be retrained. Now we're just writing code, right? Here, let me just. No. We probably want to get out of here. I'm getting that look. Like we only have so much tape in the camera.
Can you include existing Java classes, for example, for such a question? There are Java classes which are including exactly this.
Oh, sure. I mean, this is Scala, so you can bring in your Java code with that. Running Java classes inside Scala is perfectly acceptable. The only part that needs to be, well, the Scala part is the part that sets up the streaming because that's how it's built. But you could take the output, you could cast an RDD into something else. Yeah, I think that's very doable. I think we have a project starting up here. So I'm gonna finish up with my example for how we would do a temperature high-low in a stream. So as my weather station, it's got a little more complicated. As my weather station is collecting data, it's going into an API receiver. That API receiver will now be a producer into my Kafka queue. I have this actually exists, and it's online, and you can download it. I will give you the link in a minute. So this producer will put into a Kafka queue for all the weather events, and then we use Akka, which is a great way to run a lot of, that's how you coordinate a lot of actors inside Scala, to be the consumer, and based on the actor model having received, I'm going to say, okay, now here's all my actors down here for doing my temperature roll-ups. And essentially what I'm doing is I'm using the temperature actor it goes to Cassandra, says, if I get like hour 22, here is the current temperature. I can go back to Cassandra and say, give me all the hours for the day, compare this new temperature with all the rest of the temperatures, give me the high and the low, persist it right back to Cassandra. So now when I'm hitting F5, poof, it just changes. You can do that in the stream. So and this is talking and it's reading data and writing data back into Cassandra. If you're going to do this in the stream, if it's going to come that fast, you should probably use Cassandra. Because it can be potentially hundreds of thousands of writes and reads per second. You need a database that can keep up with the stream, and that's why you see a lot of people using Cassandra for that. So, like I said, you could do this at home. You could do it tonight. What time is it? It's only 9:30. You've got plenty of time. So, this is on GitHub.
Is that your last slide?
Yeah, a couple more. I was going
I'm
fast.
sorry, I don't want to be rude. Just asking.
Too late. That's all right. That's cool.
Does anyone know
All right, fine. I'm leaving.
what is the number to expand
All
the
right.
party?
So this is killer weather with no E in it. That's the only domain name I can register. So, and these are killer weather is an example. It has every bit of code. Helena, who wrote she wrote all the code. She's the person behind our Spark, one of the people behind our connector. She works on our engineering team. She's also an Akka committer. If you want to see how to do this right, she did it right. Okay, so just wrapping up here. So Databricks, DataStax. Databricks is the enterprise company for